It's a pleasure to introduce Bernd SIEBERT from Austin, who will be giving the last lecture of this morning, which is going to be about mirror symmetry via symplectic monodromy toward homological mirror symmetry for intrinsic mirrors.
Okay, thanks. Yeah, thanks for the invitation also. I'm very happy to be here and honor Tian's influence on my work and on mathematics as a whole. So this talk is about ongoing work with Tim Peru. It's a larger project, but it's also a spin-off of my long-term program with Mark Rose on mirror symmetry. There are many other major influences, maybe worth mentioning. There are a number of names. People in the know will probably be able to identify what kind of influences these are along the talk, but I should maybe mention Mohammed Abu Zaid's influence, who I talked to and discussed this topic more than 10 years ago, and along a slightly different route, and it kind of went dormant. And when I moved to Texas, I started with Tim again, and he suggested a slightly different route. But I should also say that none of this, all my involvement in mirror symmetry and Gromov-Witten theory and so on, would have been possible without Gang Tian introduced me to Gromov-Witten theory in 1993. I mean, it's actually very fitting that this is a conference on geometric analysis, whereas this is talk probably a little ill-placed. But I had the plan to become a geometric analyst. Wanted to go back to a topic I did in my diploma thesis in Göttingen. And then I got a little bored with after the thesis, with the topic my advisor Hans Grauer gave me. And I wanted to go back and follow a suggestion by de Mailly on Griffith's positivity for ample vector bundles. So I had this project from the German Research Foundation, and I visited Tian in New York to work on it. And by the time I was already pretty stuck, he also didn't have an immediate idea, but he was working on quantum homology and Gromov-Witten theory with Young-Min Ran at the time. And that's how I got into the topic. And in the following, I don't know, something like in the period 1993 to 2000 or so, we had a lot of fun together, and at least I had a lot of fun. I hope he had a little fun too. And I really learned so much working with him. And I certainly wouldn't be the mathematician I am today without his influence. So thanks, Tian. So here was tried. So the setup is we start with normal crossings degeneration of Calabi-Yau varieties. Let's say analytic over disk or algebraic over discrete variation ring. And we want this to be a maximal degeneration. That just means that the center fiber has at least one zero-dimensional stratum. So I've tried to draw here degeneration of a quartic in this example down here, where I have shifted all the interesting topology to infinity, so it actually comes out as a nice picture. And with Mark Rose, I defined a ring associated to it, whose projective variety produces the mirror geometry. That was a dream result for many years. So most topics in mirror symmetry start by some ad hoc construction, but not what would be natural for an algebraic geometer to start with. And we finally can do it. So you start with a maximal normal crossings degeneration of proper Calabi-Yaus, and you get a ring. And so how does this work? It's a degeneration of a pretty large base ring typically. So what is this? The holomorphic curves in the total space of this degeneration, they of course are contained in fibers because it's a proper map to something Stein, form a submonoid of the homology class, a single homology, typically denoted NE of X0. And the ring as a module is an algebra over this base ring that you form by taking these as exponents. So the notation means that you take take formal power series with powers in these curve classes. And there's one generator for each contact order. So what is this? So a normal crossings degeneration has what is called a dual intersection complex, where you associate one vertex for each irreducible component and then builds the Symplectic complex according to the pattern these irreducible components intersect. So these have integral points. The integral points are just the vertices. And then when you rescale by d, you get more integral points, and that's this notation. So these are the integral points of the d-scaled Symplectic complex, and you get a graded ring with this d and one generator for each such 1 over d integral point. So I'll explain to you that these are really contact orders of holomorphic curves. Think of holomorphic disks in the total space, contact orders with the irreducible components of the central fiber. Okay, so generically, you would think, okay, so I meet an irreducible component in a smooth locus, that just gives an integral point. But if you have multi-sections, so the composition to your disk is a default cover, then you would fall into the more singular locus, and that gives these 1 over d integral points. So for example, for the quartic above this kind of equation, you would get the B, that dual intersection complex, the boundary of the 3 simplex. So of course, everybody can write this down. That's not anything deep. The cool stuff comes when you want to make this a ring, so you need to define structure coefficients. And I think it's a huge joke of the history of the evolvement of mathematics that the answer to these questions goes back to the very beginning of mirror symmetry, where people observed a relation between Gromov-Witten invariants on one side and period integrals on the other. So the mirror geometry is a kind of Gromov-Witten invariant. So these structure coefficients are certain Gromov-Witten invariants, but not the ones we could have written down in the early 1990s. So these are counterholomorphic coefficient X with contexts of orders P and Q, and then minus R with X0. And I'll have to explain what I mean by this. So here's these contact orders. Technically, you need what are called logarithmic and punctured Gromov-Witten invariants. I'll skip all the details. You enhance, in Gromov-Witten theory, you look at maps from nodal curves. These are called stable maps. And you enhance these with what is called a logarithmic algebraic structure to impose contact conditions with the divisor. So how does this come about? If your curve, let's say these Niels parabola, is not contained in your divisor, you just get the usual contact orders. So this would be, in this case that I've drawn, contact order 2 with y equals 0, contact order 3 with x equals 0, okay? But logarithmic algebraic geometry allows you to also talk about these contact orders if your curve falls into the divisor. So think of rescaling that whole thing and take a limit where this Niels parabola falls into the y equals 0 divisor, then it's impossible to make sense of, contact order doesn't really make sense, but logarithmic algebraic geometry allows you to formulate this. So, and that thing also works with negative contact orders. So to give you an idea of what this is, let me just discuss this example. So let's look at negative contact order, of course, can't happen in transverse situation. Positive contact, that's always positive, non-negative contact, right? In complex geometry. But if you have a contracted curve, so let's just take C2 with these 2 divisors that we think of as part of the central fiber, and you just contract the whole component to this point, and I'm putting here 3 points P, Q, and R, like I wanted to do here, right? So, and then let's take contact orders P, Q, and R as written. And then the log enhancement, so I want contact 1, 1, minus 2 with the x-axis, although I'm just contracting the whole thing, and so on, and with the y-axis would be 0, 2, minus 2. And then the log enhancement, which is provide isomorphisms between line bundles. Okay, so the first one is the x-axis that has contacts 1, 1, minus 2. You see a change of sign. And then 0, 2, minus 2 is over here. Okay? So that's all I wanted to tell about these logarithmic Gromov-Witten invariants for this audience. So there is a way to enhance Gromov-Witten theory with negative contact orders, and these produce these structure coefficients. So that gives a ring. The big result is that's an associative ring. That's a little hard to prove, but let's take it for granted. And to give you some idea of what this does and how this relates to previous mirror constructions, let me just look at one a little less degenerate example than the quadratic. So let's take a small resolution of a maximal degeneration of hypersurfaces of degree 222 in P1 cube. Then the central fiber x0, you degenerate to a union of coordinate hyperplanes in P1 cube. That's 6 copies of P1 cross P1 glued together like the boundary of a cube. Okay? And the mirror geometry, the dual intersection complex takes a dual polytope. So that would be an octahedron like I drew here. And the mirror geometry would actually be a family of mirror K3 surfaces. And more generally, you can do something similar in toric varieties. You could start with a maximum degeneration of complete intersection Calabi-Gauss, like the stuff people did for many years in mirror symmetry constructions. And then this mirror geometry we would compute intrinsically is actually the Borisov mirror, but written in canonical coordinates. So the takeaway, if you didn't understand anything, is that the intrinsic mirror ring is really a degree 0 relative quantum cohomology of this maximal degeneration x comma x0. Okay, so relative to the central fiber, you look at the total space. Okay, so that's all for algebraic geometry, I promise. Let's go to symplectic geometry. There is, when you have a normal crossings degeneration or any family, there is something called the symplectic monodromy. And that's simply due to the fact that if you have on the total space, you have a closed 2 form, each fiber a non-degenerate closed 2 form, or at least it's non-degenerate on the fibers, it has a perp in the total space, okay? And that provides a connection for this fibration. And you can use parallel transport for this symplectic connection. And if you do this along a small circle around the central fiber, you get what is called the symplectic monodrome. And there, for any symplectomorphism, that's a symplectomorphism, okay? So for any symplectomorphism, you have Hamiltonian Fleur groups. And that's late 1980s, early 1990s technology. Nothing virtual or so on necessary. Just work with pseudo-homomorphic cylinders and so on, as Fleur did. And they produce these Hamiltonian Fleur groups for each power of this symplectomorphism, okay? So the coefficients of these Fleur groups are in the Novikov field that counts the areas somehow, the symplectic areas of these cylinders. And it comes, so it's a module over this Novikov field or a vector space, and it has, but it also has a ring structure. It's called the pair of pans product. So schematically, that looks like this. You take a pair of pans, so that's a disk minus two disks inside, and you take pseudo-holomorphic maps to what is called the symplectic mapping torus. I'll explain in a second. Fulfilling the Fleur equation for some Hamiltonian perturbation, this Hamiltonian vector field, and with asymptotics given by these fixed points. So now we have fixed points P, Q, and R, okay, of this symplectomorphism that you can feed in to this pair of pans at these 3 ends, and you look at pseudo-homomorphic curves to this pseudo maps to this thing, and you count it, and that gives the structure coefficients. So what is this symplectic mapping torus? You take X cross, I would like to think of this as C star. That's kind of the log of the radial coordinate, and that's the angular coordinate, and then you glue together with a twist by this phi to implement this as a symplectic monodromy. Okay, so you have also a ring coming exclusively from symplectic geometry associated to this normal crossings degeneration. Okay, so that looks kind of tempting, right? So we have two natural rings associated to this geometry. There should be some relation, and that's the conjecture that Tim suggested, or which is kind of in the air here, namely that up to massaging the coefficients, the base ring, so doing a base change from this big ring to the Novikov field, they should be canonically isomorphic. So note that this x to d, although we started with algebraic geometry, is really the symplectic geometry side of mirror symmetry, okay? And then you take the proj, the corresponding family of projective varieties given by this ring, and that will be the complex geometry side, okay? There's one curious thing here, right? So the R was naturally bigraded, namely by D and by this P, or I had a refinement of the D grading by this P. So how do we see this in the symplectic monodromy ring? That's simply if you compute the first homology of the total space of the complement of the total of the center fiber in the total space, you see it's naturally given by this kind of thing. Now, here similarly, we have these P, Qs, and Rs. They're kind of loops at infinity or at zero, around zero. So they have a first homology class, and that gives the additional grading. Okay, so both rings are similarly graded, and as a module, they are obviously, that looks very close. I mean, that could still be big. We don't know this. That's part of the problem. But conjecturally, these are just one-dimensional. Okay, so in particular, that would be the outcome of this conjecture. I should mention here that Ganatra and Pomigliano, much more in this spirit that I was trying to work, that I discussed with Mohammed Abu Zaid in, I don't know, 2012. They looked at the symplectic homology of the complement of a divisor in an anti-canonical divisor in a logarithmic Calabi-Yau situation or a Fano situation, and they proved a very similar result, but only as modules without the ring structure. Okay, so they have these, and symplectic homology is kind of, yeah. I don't have time to explain this properly. Okay, just want to mention it. So, okay, so maybe let me stop here before I explain to you why this is not just another way to construct intrinsic mirrors, but why this helps in doing homological mirror symmetry. Are there any questions at this point? Are we all good? So we have the intrinsic mirror ring, right? Algebraic geometry, punctured Gromov-Witten invariance. And then we have the symplectic monodromy ring, just Floer homology and pairs of Pan's product. Okay? So the perspective is, how does this help to prove homological mirror symmetry? So homological mirror symmetry is, in my mind, a rather complicated statement. I mean, even writing it down precisely involves many pages of refinement. So morally, you want to say that the Fukaya category is the same as the derived category. Okay, so that's a kind of elevator pitch version of the thing. But then, if you think more closely, all hell breaks loose, right? So the derived so you want to look at the derived category, but that's just a triangulated category, while the Fukaya category is not, it's not even a good category or something, and has all kinds of problems, and it's certainly not triangulated, but has naturally an A-infinity structure. So you first have to kind of upgrade both sides. There's a natural A-infinity structure that is what this DG is good for, and there is a way to turn this into a triangulated category and make it into a kind of nice triangulated A-infinity category that is given by this, what is called the Karui completion twist pi. I don't want to explain this, but both sides are just involved, and fortunately the good news is we don't need to worry about this too much. We can prove that statement, of course using hard work of other people, by checking a lot less. So let me try to explain this. Why this is actually, the statement is actually boils down to something a lot more manageable, namely on the ring level, essentially. So the complex geometry side is kind of easier. It should be very familiar to all these people familiar to Keller geometry in this room. So first, this URF category is split generated by parts of an ample line bundle L. So that comes down to saying that each coherent sheaf has a finite projective resolution by parts of an ample line bundle. Okay, that's not so hard to prove on a smooth space. And then, so to understand this side, it is enough to understand not this kind of complicated category, but really to an A infinity algebra that's given by this kind of thing. So you take parts of the ample line bundle and take the cohomology, and takes a sum, direct sum over everything. Okay, and that has a natural A infinity structure. Then you notice that for Calabi-Yau, good things are happening, namely, only the summands survive where either this thing here becomes, well, P is 0 and D is non-negative, so that's just the usual homogeneous coordinate ring, okay? And the other cases that is non-trivial is the top cohomology of strictly negative parts of D. Okay, that's the only thing that survives when you apply Kodara vanishing. So, and then there's this astonishing result by Polishuk who shows, well, how many L infinity structures are on this if you know the ring structure on that guy, okay? And there's a unique up to isomorphism or up to scale A infinity structure. So a unique up to isomorphism, non-trivial A infinity structure. So that makes this statement a lot more manageable because we know what this is. The A infinity structure on this one is kind of easy to see, okay? So we need to identify something similar on the Fukaya category side. So how would that work? The first insight is, that comes from the SYZ perspective, that the action by monodromy phi on this Fukaya category of a general fiber. Yeah, you have X, that was a general fiber of our degeneration. We have the symplectic monodromy. That's a symplectic morphism, so it will act on the Fukaya category. That is mirrored to tensoring with the ample line bundle that you get on the Proch R. Okay, so that's well known. So we get these phi d of L kind of, but we would need some L to start with. The analogs are homological mirror of the structure sheaf O. Okay, so obviously, for homological mirror symmetry to hold, there must be some mirror object to the structure sheaf, and that would be, in the SYZ perspective, a Lagrangian section of your SYZ fibration. So let's assume we have such a Lagrangian L, and then we would have to show that applying these monodromy, parts of the monodromy to L, split generates f of x, Fukaya category. We need some analog, symplectic analog in Floer theory, so an analog in Floer theory of Kodara vanishing, which says that L phi d L has non-trivial Floer cohomology only in the range given before. And then we have to show that our intrinsic mirror ring, base change to the Novikov field, is isomorphic to this kind of Floer theoretic ring that you get from Lagrangian Floer theory. This is Lagrangian Floer theory, okay? Okay, so then there was some work in terms of going back to Mohammed Abu Zaid and then Peretz Sheridan and Ganatra. They all have worked in showing when can we assume that one is true. And there's I'm stating here the theorem by Peretz Sheridan, there's a similar result by Ganatra, that it's enough to check that X and Y will be homological in mirror if and only if there exists a full A infinity subcategory of the Fukaya category, quasi-equivalent to RK tilde. So RK tilde is this guy here, right? The R tilde base change to the Novikov field. Yeah, so Okay, but now you use Paul-Schock theorem, and you can replace RK tilde, this statement, by RK. That's exactly the statement I was, or the conjecture with Tim, I was stating 2 slides ago. And then compute a single Maslov class, Maslov product, okay, to show that they are actually the same. And so what are candidates for L? Well, that's getting a little difficult here. So the best I can do at the moment is, if X itself, X was a symplectic cycle, if X itself is a mirror coming out of our program, we can take the positive real locus. That's a distinguished Lagrangian kind of section of the SYZ fibration. And that would have all the good properties for Floer theory that Fukaya and co-authors proved. So the analog of 2, this vanishing, would then should then follow. We don't quite know how to do this, but it all looks very hopeful, from a good symplectic model for the symplectic monodromy or the family. And then to show 3, well, we have a map from RK isomorphic to S of phi, so that was Hamiltonian Floer theory, right? The symplectic monodromy ring, but there's a closed open map from the symplectic monodromy ring to the Floer theory of L with respect to phi. So this was this kind of Lagrangian Floer theoretic object. And you can do a low energy limit of the energy spectral sequence to show that this is an isomorphism. Okay, so I'm almost done with time. So maybe I have a number of slides that I wanted to indicate how to we might be able to prove the conjecture. Let me just give that kind of basic picture here, and then I'll stop for questions. So the basic principle, and that was certainly done also in the air when I talked to Mohammed many years ago, and is present in the work of Ganatra Pomigliano, is we need some kind of Punichen Salomon-Schwarz homomorphism. But the version we need is what I would call the log PSS homomorphism. That goes from the intrinsic mirror ring to the symplectic monodromy ring. And how would that come about? So I've tried to draw a cartoon here of this total space of the degeneration. And let's say we take an integral point, an integral point of our dual intersection complex, and fix a point here in the corresponding, in the smooth locus of the corresponding component. Then let's assume we have a good symplectic model. On this, near that thing, the whole thing is a product, okay? And there's nothing really interesting happening here on that slice. So you can fill in a disk that extends, actually a copy of C, okay, that extends all the way to infinity as a section of that pi. And that will actually be a fixed point of the action of phi, right? So if you look at a good symplectic model, you would have a very degenerate phi. It would just be constant on that part, okay? A big chunk of the central fiber. So hence you can that is just a trivial map. So that would be this psi in the easiest case. You can write down this map in great generality, okay? So you look at pseudo-holomorphic sections or multi-sections, depending on what p is, of this pi, and then see that on one side you get these fixed points of phi to d. On the other side, you get these contact orders that enter into this ring. And so the point is, of course, that the fixed points of this phi to d correspond to these asymptotic loops. And then there's a bit of a virtual aspect stuff going on where we intend to use the Abu Zaid MacLean-Smith results that Mohammed talked about on Monday, when was it, yesterday, right? And some complication I don't have time to explain, Um, and then one has to show that it's actually an isomorphism, and we have some ideas on how to do that. But that would be the kind of a scheme of proof. So maybe I'll stop here and give occasion for discussion.
Thanks, Bernd, for the very interesting talk. So are there any questions?
So you mentioned something about quantum cohomology at the end of, and I had this discussion with Kenji of what is the right notion of quantum cohomology in the relative setting.
Say it again.
You mentioned something about quantum cohomology in earlier slides, and this morning I had this discussion with Kenji. What is the right notion of quantum cohomology in the relative setting?
The right notion of quantum cohomology in relative setting?
Yeah.
Well, okay, yeah, maybe I could say this. So these kind of intrinsic mirror rings that I wrote down with Mark should really be thought of a degree 0 relative quantum cohomology, okay? So there's only, if you paid attention here, there's always just this 0 up here, right? So a full-blown, I mean, of course, quantum cohomology in degree 0 is boring typically, right? It becomes only interesting if once you put in a divisor. And that's the thing we didn't know or missed or whatever many years ago, right? 30 years ago or so. So that's a new thing. I think what your question is pointing to is, so what will happen to if you want to, not here, if you want to, I didn't say this here, if you want to connect, so have a full-blown relative quantum cohomology ring, okay? So let's say we have a symplectic variety with some divisor, normal crossings divisor. There are all these kind of classes that live on the divisor that should interact with your holomorphic curves. And yeah, so this is what that was on the slide that I didn't get to, on the next slide here, right? So this is a project I'm just doing with Mark to generalize our results or associativity result in degree 0 to a higher relative quantum cohomology, to properly define relative quantum cohomology. So you said Kenji has some, I think
he mentioned that you have some comments.
Yeah.
But Kenji's not. So
he's not here, yeah.
I kind of asked the question.
Right. It's actually difficult because it won't be a cohomological theory. So you actually need to work on chain level. So we will also use this opposite McLean-Smith, upgraded to a chain level thing and so on. So Mark and I are a little intimidated, but we'll push it through.
Are there other questions? Well, I have a question. Could you explain what the positive real locus means?
Right, so yeah, it's difficult to see from here. So so there's a bit of a problem here. Well, let me see. Where is it? So I have, not sure if I have it anywhere. So if you take this ring here, well, I wrote C here, but of course you could write Q, rational, or yeah. So that thing actually comes from all the Gromov-Witten invariants are real numbers, of course, right? So that is defined as real numbers and has a designated real locus, okay? Sure, so the whole thing is real, or comes from a real degeneration. Now, in the situation, in the kind of, yeah, so the problem is that the Gromov-Witten invariants are typically not positive always, right? They can be negative. So that spoils the kind of, you can't make sense of a positive real locus. But we do know it does make sense in our older constructions that was published in the Annals in 2001. The paper is from 2007, but was published many years later, where we have these kind of more synthetic construction of mirror pairs, which are a special case of this. Okay, so we know many cases, especially those that fit into the Baturev-Borisov world, complete intersection in Calabi-Yau's, where our degenerations actually respect a positive part. So there's this wall crossing, and the wall crossing is always positive real. So there is actually a distinguished connected component of the real locus that in local coordinates always has positive real entries. So that would be the positive real locus. Does this answer your question a little bit?
So, for example, from this construction, you wouldn't wind up with sort of like the dwarf pencil, the standard.
What would be wrong with the dwarf? Let me see. No, we would. We get so what's wrong with the dwarf pencil?
I mean, there, like the real locus is just.
It's not right. So let me see. No, I think the dwarf pencil should be fine. We have a positive real locus in dwarf. Is that maybe I'm using slightly different coordinates than you're thinking of. We can discuss later, maybe.
Okay.
But the dwarf pencil fits into Bhattacharya of mirror symmetry, right? So it should be fine.
Is there like a positivity conjecture similar to what exists in relation to skein algebra? Do you have any positivity conjecture for these coefficients under certain
It's wrong. We know we have examples where it's negative. It's just plain wrong. I mean, an interesting question for symplectic geometers that I have in my mind is, I mean, okay, so we all have a real locus, okay? So what would be the mirror object of the real locus? We may not have so that would be a vector bundle of degree 2 to n, yeah? What is it? And could we use that to prove homological mirror symmetry? And I have no idea.
Thanks. Are there any other questions? Okay, then let's thank Bernd again.